So today we are looking at the last unit for the semester. You're halfway done with AP Chemistry. Can you believe it? Y'all are just ridiculously quiet. It's a Monday after Thanksgiving. Everyone have a good break? Everyone sleep? Eat? I think I watched like 8 movies, or if not more. Anyway, so we are looking at liquids, solids, and solutions. And before we actually delve into those things specifically, we need to look at what goes on between those molecules and the relationship between those molecules by looking at something called intermolecular forces. So here we have the mention of intramolecular force and then the description of intermolecular forces. I know you all did that POGIL activity on intermolecular forces in class on Tuesday or over the break, so hopefully this will be a little bit refreshed. Intramolecular forces are the forces that exist within the actual molecule itself. Intermolecular forces are forces that occur between the molecules. What is another one-word name that's synonymous with intramolecular force? One word. Force within a molecule. Oh my God. What? Bond. Bond. This is a bond. All right? So bonds are intramolecular forces. Bonds are much stronger than the intermolecular forces we talk about. We're talking about 1% the strength. Intermolecular forces have about 1% the strength of actual bonds. Okay? So intramolecular forces are the forces that attract molecules to each other. What would our world be if we had no intermolecular forces? Imagine it. What would it be? Molecules were not attracted to each other at all. Yeah, what would that be? Scattered out. Gases. We'd be a world of gases. Okay? So since we're not a world of gases, we know that there has to be some sort of attraction between different molecules. When we're talking about intermolecular forces, we're assuming that there's molecules, which is kind of inferring that we're dealing with covalent compounds. Ionic compounds have no intermolecular force. Why? Are they molecules, ionic compounds? My questions aren't rhetorical. I'm expecting a response. Let's try that again. Why don't ionic compounds have intermolecular forces? Exactly. He walks in, not hearing me talk, and answers, and you all just sit there. There's 29 of you in here now, and the person who just walked in answered my question. It's going to be a great day. I appreciate it. I'm not going to yell at you for being late now since you actually answered my question. Should be excited. You saved yourself. All right. So anyway, intermolecular forces exist between molecules. Ionic compounds are not molecules because they don't share electrons. Remember, ionic compounds are strictly opposite ions attracted to each other with electrostatic forces. Those aren't molecules. So there's no intermolecular forces. These are all crystals in this big old lattice. So when we're talking about intermolecular forces, the point of me saying that is we're not referring to ionic compounds. So anything I'm talking about now doesn't refer to that at all. Okay? What I'm referring to is the attraction that makes things closer, molecules closer together in solids or in liquids. So here I have some molecules of water, and see how they're attracted to each other? So this kind of looks like ice would look. If I am overcoming an intermolecular force, I am separating that electrostatic attraction. What's making these electrostatically attracted to each other, these molecules? Why are they attracted to each other? Well, they have intermolecular forces. Why do they have intermolecular forces? Because I heard it. Because they're polar. They have dipole moments and an asymmetrical distribution of charge on themselves, so that gives them partial negative and partial positive sides, which then makes them attracted to other molecules. If I were to take this, put it in a beaker and boil it, the molecules would separate. Are bonds broken? No. Intermolecular forces are overcome when we have phase changes. We do not break bonds. How would I break bonds in water? How would I make this H2 and O2? I'd have to run electricity through it at minimum, okay? If I were to heat water, I could heat it all day long. What's going to happen? It's just going to go to gas, and the molecules are going to spread out farther and farther and farther apart. I'm not going to break these bonds. Super strong bonds, intramolecular force, versus this attraction, intermolecular force, okay? All right, so we're going to talk about the difference, again, between intra and inter. Here, see these dots? Those aren't actual bonds. This is our intermolecular force, our IMF, which is just an electrostatic attraction. The actual intermolecular force are the bonds. Intramolecular force is the bond itself. Strong, still strong, but not, again, like 1% of the strength of that actual bond. This is an electrostatic attraction due to the polarity and the dipole moment of each of these molecules. Hydrogen has a partially what charge? Hydrogen. Positive, while oxygen has a partially negative, so those are attracted to each other intermolecularly. Got it? So important you know the difference between. A few years ago there was a question on the AP, true or false, when you boil water, bonds are broken. False. And I'll tell you why people said true. And it's because the stupid person who named these intermolecular forces, which is really frustrating. So again, when we have phase changes, all we're doing is separating the molecules. And to do that, we have to overcome the intermolecular force. So some energy has to be in there to split those up, to break that electrostatic attraction. And the more energy we add, the further apart the molecules will go. And this is a physical process here. We're not breaking bonds, so it's not a chemical process. So anytime we change phase, it's physical. And you should know that from when we did physical and chemical changes. All right? So changes in state are due to changes in the forces among the molecules rather than those within. So we are not breaking bonds. We're overcoming electrostatic attraction or intermolecular forces. And I know I'm sounding like a broken record, but I'm doing it for a reason because I promise someone's going to say something crazy on the test. So let me just do a real little, I have a blank spot here. You can write it anywhere. Little recap of the intermolecular forces you covered in your POGIL activity. IMFs you can use the term IMF on the AP if you first state it, and then after that, you can use it continually. IMFs are also known as van der Waals forces. These are all intermolecular forces known as van der Waals forces. There's two main kinds. There's dipole-dipole, and then there's London dispersion. Who remembers what kind of molecules are attracted by dipole-dipole interactions? What? Polar. Who remembers what kind of molecules are attracted through London dispersion? These are all covalent, nonpolar. Okay. Now, dipole-dipole specifically has two intermolecular forces, plain old dipole-dipole, and then a very strong special dipole-dipole called what? Correct, hydrogen bonding. Hydrogen bonding is not a bond, and this is why students say bonds are broken when water's boiled, because they're saying those are broken. It's not a bond, okay? It's still an electrostatic attraction. They're calling it a bond, though, just because it's a lot stronger than plain old dipole-dipole. Hydrogen bonding specifically occurs when hydrogen is attached to which one of three? Oxygen, nitrogen, and fluorine. I say NOF. Okay? Due to the large electron, I don't want you to use this in your explanation. Okay? Hydrogen bonding is stronger because it's all you have to say is there's hydrogen bonding in this molecule because hydrogen is attached to one of these. in a polar molecule. Again, these have to be polar, and if it's this attached to one of those, it's hydrogen. That's your explanation. But why is that the case? If you notice, these are your three most electronegative elements, okay? So what's the word I'm looking for? What? Well, the difference, the discrepancy in electronegativities between the hydrogen and any of those is so big, it affects the polarity of that entire molecule pretty significantly, making the electrons even more asymmetrically distributed, okay? So why they chose the cutoff here and why these three, I don't know. It's just numerically they decided, okay, this is the point we're saying hydrogen bonding exists. This is all arbitrarily created by somebody, all right? So this is much stronger, but again, both of these molecules are polar. So the first thing you need to do when you're trying to figure out what kind of intermolecular force you have is to determine what the polarity of the molecule is. How do I do that if I have a formula? Just look at it? What do I have to do to find the polarity of something? You just had a test on it. Yeah, draw out your Lewis dot structure. Use your VSEPR. Okay, decide if there's any lone pairs on it and if it's a polar or nonpolar molecule, or if there's something different attached to the central atom making it polar. Okay, you're going to have to first stop and look at it. You can't just say, oh, there's a hydrogen in it and an oxygen, so it's got to be hydrogen bonding. No, you got to check what the polarity of the whole molecule is first. All right, so stop, draw out your structure, and then make your decision. Once you decide if it's polar, the primary intermolecular force is dipole-dipole. Is it going to be specifically hydrogen bonding? I don't know. You have to see if this is true. Now, if it's nonpolar, easy enough. The only intermolecular force that exists is London dispersion. What I need you to realize about London dispersion, though, is that it's in everything. And I'll explain why in a minute. But when we talk about water, we don't say, oh, water has hydrogen bonding and it has London dispersion. It's kind of a given that it has London dispersion. Why do you think we only say it has hydrogen bonding? Because it's the strongest. It's the primary force that exists. So let's take a look at just our London dispersion first. Again, this exists in all molecules, but it's the primary force in nonpolar molecules. So, nonpolar molecules have no dipole moment, right? So how are nonpolar molecules attracted to other polar molecules? Why aren't all nonpolar molecules gases? And that's the question that you have to ask yourself. So for instance, I like to always go down the periodic table, Cl2 to Br2 to I2. Looking at the periodic table, look at the colors. What's happening to the state of matter as we go down that table? It's going from what to what to what? Gas to liquid to solid. Those are all nonpolar molecules, so all of these have London dispersion forces in there. Why would this guy, since it's solid, is going to be stronger or less intermolecular forces? Stronger. So there's something about this guy making it more attracted to other I2s. Any ideas? It's not a factor of electronegativity. That's a good idea, but it doesn't work that way because if we're talking about bigger molecules, it's not. Okay, large. It has to do with the size. If you look at chlorine, how many electrons does chlorine have around it? 17 times 2, so 34-ish, right? And iodine has 103. Do we agree that's a lot more electrons, 30-something to 100-something, right? So what makes nonpolar molecules have a dipole moment? At one point in time, they have to be attracted to each other, so something is making them have a dipole moment. It's basically just a random occurrence when these molecules bump into each other. I call it the squishiness of the shell. The real term is polarizability. The more electrons you have, imagine this running into some other I2. Do we not agree that the more electrons you have, the more probability you have for a huge shift of charge? Right? So imagine this running into someone over there. All its electrons are going to go to one side. At that moment in time, that side's partially positive and that side's partially negative. Just for an instantaneous moment. That's why we call it an instantaneous dipole. When you have fewer electrons, do you see how the shift is not as dramatic? Right? So we get a shift, a little bit of a shift, but not as dramatic. So I never want you to say size. I want you to talk about number of electrons. On the AP, they won't give you credit for saying I2 has a stronger intermolecular force than Cl2 because of its size. They want you to say because it has more electrons and is more polarizable. When I use the term squishy, that's not an official term, but I just imagine this big fat shell of electrons squishing from side to side as it's moving and bumping into sides of container and bumping into each other. And that shift of charge is giving it a dipole that lasts for just a second. And while this is going on, it's going to be attracted to other I2s for that moment. So that's why I2 is solid at room temperature and Cl2 is gas. All right? So does that kind of explain why everything has dipole-dipole? Because everything has electrons, and every molecule has random motion, and every time it hits the side of a container or other molecules, there'll be a shift. Is it the primary force in dipole-dipole? No, that polarity is really dictating the shape of that cloud. But in this case, this is the only thing dictating the melting point. Yeah? Well, it doesn't matter. It can be on the left. Yeah, just however it bumps into something. I chose because if I bump here, my electrons are going to go that way, and so that would be my partially negative side. You're never going to have to really worry about that. I mean, they might make you draw a cloud, but they're not going to say, oh, it runs into this wall, so you don't have to worry about that. Just know the side with the more electrons is the partially negative side. Okay? So that's London dispersion. Dipole-dipole, again, are between polar molecules. And this is just stuff that has dipole moments. So when we do like HCl gas, we have a dipole moment that way. That makes it a polar molecule. Or if we have CHHHCl, that's going to have a dipole that direction, making this side partially negative. So this is a polar molecule. Therefore, it's going to undergo dipole-dipole. Why isn't this one hydrogen bonding? There's hydrogens in there. It's not connected to a N, O, or F. It has to be specifically connected to an N, O, or F. And it has to be connected to the N, O, or F. I don't care if this was an F. It's still not hydrogen bonding. It has to be attached directly to one of those three to be in the hydrogen bonding category. Okay? So this dipole will make, and if I do the overall dipole, this is the partially negative side, this is the partially positive, and that's going to align accordingly with other CH3Cl molecules. Hydrogen bonding then is a strong dipole-dipole, and again, NOF, nitrogen, oxygen, fluorine. Got it? So, how does this affect things in the melting point and boiling point world? We're going to go over this a lot more specifically when we get to colligative properties, but for now, why would something with a stronger intermolecular force have a higher boiling point? Just simply stated. Anyone? Chris said it's harder to break those bonds. No! That is so wrong. What's wrong with what he said? Why do I want to jump out the window right now? We're not breaking bonds. It's harder to overcome those forces. Or you could say it's harder to separate the molecules because they're more attracted to each other. The stronger the intermolecular force, the more attracted the molecules, the higher the melting or boiling point. Okay, we have to put more energy in something that's got hydrogen bonding than I do into something that's got London dispersion to spread those molecules out. So looking at some of these, H2O versus H2S, H2SC, I'll tell you right now, all of those have the exact same structure. They're both 2 bonds, 2 lone pairs. okay? Why is H2O so much stronger? It's got hydrogen bonding as an intermolecular force, okay? So it's going to have the highest boiling point. Well, let's talk about these then. Notice we're going down the periodic table. These all are polar. They all have the same shape, so their polarity is pretty much the same. What is making their... So they're all polar, but what type of intermolecular force do we know for sure is here? Well, London, yeah, but dipole-dipole, right? So all these are dipole-dipole. But what's making their boiling points different? The polarizability, which is affecting which force? Yeah, remember, they're all pretty much the same in the polarity world, okay, because they're the same shape and all. But what's making them more polar then is those extra London dispersion forces. And this one is going to have the highest London dispersion force due to the size, the extra electrons. They're still dipole-dipole, and in no way am I saying London dispersion is the primary force. I'm not saying that. I'm just saying this is not a huge difference in boiling point, really. This is like negative 50 to 0 compared to negative 50 to 100. This is not huge. Okay, so what is making that subtle difference? It's the extra electrons creating a higher London dispersion force, which is adding on to that dipole-dipole. Okay, so all of these peaks here at the beginning, bam, bam, those are so much higher because both of those are hydrogen bonding. Okay, and then the same thing, our molecules are getting larger, and so yeah, they're all dipole-dipole, but what's taking over there is extra London dispersion, making them a little bit higher. Okay, so here, these are all London dispersion. That's nonpolar, this is nonpolar, this is nonpolar. So London dispersion is the primary drive there. What's making it increase then? The polarizability, the London dispersion as well, here, straight up. Kind of got it? Suggest you read your textbook on this if you're still stuck. All right, so this is the same sheet you got with your POGIL activity. It's just a synopsis of everything I went over. So feel free to read through that if you need some more. So let's answer some of these questions. Which molecule is capable of forming stronger intermolecular forces, N2 or H2O? Explain. H2O. Why? It has hydrogen bonding. When you do something like this, the expectation is for you to describe the intermolecular forces in both things, not just the one they're asking, because you need a basis for comparison. We know this is stronger. Why? Because N2 is nonpolar. We know what its intermolecular force, we know what its Lewis dot looks like, right? And we know H2O is polar and it has hydrogen bonding. So this is hydrogen bonding. So state both of them and say because hydrogen bonding is a stronger intermolecular force, well, they're not asking about boiling point. Say hydrogen bonding is a stronger intermolecular force. Okay, but you got to state both because they'll go, well, what about the other molecule? All right, draw two Lewis structures, and I'll help you do the drawing. You're never really going to be asked to draw them out. You will have to compare drawings, though. So I wouldn't force you to, but I'm going to go ahead and draw one of them. Here's an example of one of these guys. Anyone else have any other ideas for the other one? Without breaking any rules? Yep, COC, very good. Okay, so these are the two possible, what we call isomers that we can get. Okay, isomers are things that have the same formula, but are different compounds, structural isomers. So looking at this, does anybody recall from Chem 1 what the name of this group is, like what this whole molecule is based on that group? This is an alcohol, good. I don't expect you to remember this. This is an ether. All right, so looking at this, compare the boiling points. We have to talk about intermolecular forces before we can talk about boiling points. What kind of intermolecular force exists in this guy here? This is hydrogen bonding. because we have an O attached to an H. And this area right here causes a dipole moment. So this half of the molecule is partially negative and the other half is partially positive. And because it's specifically a polar molecule with hydrogen attached to N, O, or F, it is hydrogen bonding. So that is going to be a pretty high boiling point. What about this one? I know there's an O. What can you tell me about the symmetry of this electron cloud? It's nonpolar. Yeah, this is a super, super polar center, right? And then nonpolar ends. So you're going to have a very, very nice, evenly distributed cloud. So this is a nonpolar molecule. So this has what type of intermolecular forces only? London dispersion. Again, hydrogen, this does have London dispersion as well, but it's not the primary one, so we don't have to mention it. If you want to, you can, but you better list hydrogen bonding first, because that's what they're really looking for. This has London dispersion forces, therefore it's going to have a much lower boiling point, which makes sense. Does anyone know what ether is used for? Any ideas? Anesthesias that they use are primarily ethers. A lot of times in those horror movies, when the guy in the parking lot goes behind the girl and puts the handkerchief on her face, that's chloroform, which is a nonpolar molecule. It can also be an ether. I think everyone just assumes it's chloroform. Chloroform is actually kind of dangerous. So if it's a doctor murderer, it's probably an ether that he's knocking him out with. Okay, so that makes it very what we call volatile because it has very, very low intermolecular forces. So it easily goes into gas, which can be breathed? Is that a word? Breathed in? This just doesn't sound right. All right. Now, this is the primary reason I want you to take your flippin' finals in this class, because nobody in last period could remember this. This goes back to ideal versus non-ideal gas law. What was the ideal gas law? Okay. What two things did we correct for non-ideal gases? Pressure and volume. How did we correct? What would the most ideal gas be in terms of volume? High or low? Low, little volume, right? So what molecules would be most ideal in respect to volume? Which ones? Big or small? So we ideally want small molecules. Pressure. Pressure wasn't directly, we didn't say, oh, the pressure is blah, blah, blah. We based it on what? Correction factors. What? What did we base this correction factor on? You looked at something that changed. What would change the pressure? No. What would change the pressure? No. You can say temperature again. I'm still going to say no. What would change the pressure in terms of just the quality of the molecule? What? No, I heard it. What? What about the polarity, though? That's what we're talking about. That's the whole point of what we're doing. How strong the intermolecular forces are. What does a strong intermolecular force do to pressure? Brings it down, because something that has a strong intermolecular force is more attracted to itself, right? So there's less collisions with the container. So ideally, we want what type of molecule for a most ideal gas where pressure is not affected? No. We want hydrogen bond? No. We want pressure not to be affected. So we want nonpolar molecules that are small. Those are our most ideal gases. So do you see why you need to review in this class? Because this is what happens when you take the AP. You've been taught all these different things, but on the AP, they'll pull something from Unit 7 and combine it with something back from Unit 3. And they'll put it together. And if you're not reviewed, you're going to have issues. So based on everyone sitting here staring at me like I'm from outer space, you need to review this stuff. And if you wait till May to review this, you're going to really be in trouble. It won't be successful. So I want you to take the final. Anyway, knowing this now, which would be the most ideal, CO or N2? N2. Why? Because it's nonpolar, it has London dispersion forces, and so it has the weakest or weaker, I should say, because there's only two we're comparing, weaker IMF. And so the molecules are not as sticky to each other, and the pressure then won't be as affected. CO, we know, is polar, and therefore it has dipole-dipole. So that's going to affect the pressure of the gas, because they're going to like each other a lot more. Got it? That is tying in a lot of chemistry there. So I'm going to go over this to an extent. We are going to cover more of this tomorrow, so just bear with me as I go through this and realize that there might be a few holes. This first one you should have no problem with. Indicate all the various types of intermolecular attractive forces that may operate. Since we're saying all, I'll stick with that. CH3OH is an alcohol, so what type of intermolecular force? Hydrogen bonding, and everything has London dispersion. Okay. Xenon as a liquid, so it's all by itself. What's making it attracted to other xenons? What, Morgan? London dispersion, because the molecules are just bumping into each other and those electrons are shifting one side to the other side, causing that polarizable number of electrons to shift. H2S, I'll save you some time. That's what the center looks like. Dipole-dipole, because this is a polar molecule. Now, I expect that you'd have to draw that if you don't realize its shape. You can't just say, oh, H2S. It's got two H's attached to S, and it's nonpolar. No, it's polar. Why isn't this hydrogen bonding? It's got hydrogens. It's not N, O, or F. CLF. No, it's not London dispersion. That's polar. No? That's a polar molecule. Okay, now this last one, don't let it trick you. What's intermolecular force? It's ionic. So there's no intermolecular force. This is a lattice. And what's the formula that controls lattice strength? QQ over R. So if we want to talk about strength or boiling point or melting point of a salt, we're not talking about intermolecular forces. They're not molecules. We'll have to look at lattice energy. Okay, so that was thrown in there on purpose to mess with your brain. Okay, so now let's talk about melting points here. Which will have a higher melting point? It's already given to you. Now the question is why? Why does CuBr2? Why is that harder to melt than Br2? This is ionic, right? So when we melt this, we're actually breaking the bonds. When we melt this, we're only overcoming what? Which intermolecular force? London dispersion. Okay, so it's going to be a lot harder. And here, when we melt Br2 solid, we're not breaking Br to Br bond. We're just separating the Br2s from each other. This one, because it's a lattice, we have to actually break bonds. So that's going to have a way, way higher melting point. CO versus SiO2, I'm going to kind of reserve this until tomorrow. This is a covalent network. And it's much stronger due to the fact it's doing three-dimensional bonding all around the center. So I'm going to say tomorrow. So we'll talk about that tomorrow. Another thing we'll talk about tomorrow is this one. What's the difference there? Just looking at it, they're both atoms. What's the big difference between an S and a Cr? One's a metal and one's a non-metal. Metals undergo a specific thing called metallic bonding. So that's going to immediately make it have a higher melting point, which we'll talk about tomorrow. Now this one I think you can answer. Two salts. We're comparing two salts. Why would one salt melt at a higher temperature than another salt? It has more lattice energy. Lattice energy is based on charge and radius. Notice that CSBr has got less of a charge and more of a radius. So it's getting hit double. It's going to have lower lattice energy for both of those reasons. CS is a +1 times a -1. And notice CS is a lot bigger of a molecule. CSBR is a lot bigger of a, not a molecule, of these two ions than Ca +2 and F-. Okay? We good with that? Now, I know it's been a long lecture, but tomorrow is also very long, and I'm really concerned about getting that done because there's a couple of videos I want to show you of some more crazy science people. So I want to do this liquid thing real quick. It's just a couple slides. Liquids, we know, our molecules are not as close together in solids, but it's still hard to compress them because they're pretty close. There's a bigger difference between the molecule space between a gas and a liquid than there is between a liquid and a solid, right? Lack of rigidity, though, what does that mean? It's fluid. I can take it and pour it into another container, and it changes the shape of the container, right? And then compared to gases, again, we have a really high density. Those molecules per unit volume are really, really close together. I need you to know just definitions of some important liquid properties: surface tension, capillary action, and viscosity. All of these are controlled by intermolecular forces. Surface tension is basically, now let's read, resistance of a liquid to an increase in its surface area. If molecules are very, very attracted to each other, like these water molecules, they're going to have a high surface tension. Okay, have you ever seen a bug walk on water? Why that's happening is because it's kind of like a skin on the top. If you flatten this little model out, you see how these molecules get together in such an aligned pattern that it could kind of make a skin? And water is also very attracted to itself. So what happens to water if I drop it on a waxed car? It beads up. And that's because it's more attracted to itself than it is to the wax. So it gets in these beads and it doesn't stay on the wax. Okay, it'll just kind of slide off. But the fact that it makes those balls, and why that area? Because that is the form, that circle that it makes is the form where it's most strategically aligned and most hydrogens can be attracted to most oxygens. Okay, it's economically advantage. Capillary action is a liquid's ability to rise up a teeny tube. That mainly depends on intermolecular forces as well. If the molecule is attracted to the sides of the wall, it's going to climb up. Okay, if the molecule is not attracted to the wall, it's going to attract to itself, and it's going to change the meniscus shape, and we'll talk about that in a minute. But again, the property of rising up a narrow tube is called capillary action, and I'll address cohesive and adhesive when I get to the meniscus idea. And then viscosity is a measure of a liquid's resistance to flow. Okay, a liquid that is very, very viscous. Give me an English word. What does that mean to you? Viscous. Thick, gooey, that kind of thing. So have you ever been getting oil changed with your parents in your car, and they ask you want an oil that's got blah, blah, blah viscosity or whatever? That's what they're talking about. And different vehicles require different viscosities. If the liquid has a really, really, really high intermolecular force, it's got a high internal friction. It doesn't want to shift around. So those are going to be your most viscous. So those are usually your larger oils. Why would big fat oil molecules be more viscous than smaller oil molecules? Have a higher molecular force. Why? More polarizable, more electrons. Okay, all goes back to IMF. So what I do need you to know, though, and you saw this when you did your pressure lab with the with the meniscus of the mercury. Do you remember that it had an inverted meniscus? That's because mercury, being nonpolar, is more attracted to itself than it is to this polar glass. So it's going to make an inverted meniscus. These forces are cohesive. Cohesive meaning more attracted to itself than to the sides. And this is going to be a convex meniscus. I need you to know cohesive, convex. Okay? This concave meniscus, think of it caved in, okay? And you'll need to know these for physics when you get to lenses. If you haven't done that yet, have you? No. Okay. So concave gives you this gives you this situation because the water's like, hey, I like this glass, and it's going to ride up the side. And so this concave meniscus is due to adhesive forces, where there's an attraction along the side of the glass. Liquids are new on the AP, this type of thing, so how much? I don't think you're going to get a whole heck of a lot. As far as your test with me goes, I'm going to ask you pretty much anything on these last couple slides. Good definitions, applying a little bit of this knowledge, but nothing like so serious. And tomorrow we do solids. So that is all for today.